Or in this example, we're going to be looking for many different features of the graph. We're going to start to analyze the graph of a given function rather than creating the function. Okay, so here I'm given the function -2 times the quantity x plus 1/2 squared times the quantity x plus 4 cubed. I've got a list of things we're going to look for. First is to list off the real zeros and their multiplicity. Well, each factor corresponds to a real zero of a polynomial. So x plus 1/2 corresponds to the real zero of -1/2. Remember, it's going to be the opposite sign of what's in the parentheses. Okay, so the first real zero is -1/2, and it has a multiplicity of 2 because the exponent on that factor is its multiplicity. So we'll say -1/2 has multiplicity 2. Over here, x plus 4, that gives me a 0 of -4. Remember, -4 would be the opposite of what's in the parentheses. So -4 is the 0, and it has multiplicity of 3, because 3 is the corresponding exponent on that factor. Okay. Part B says, does the graph touch or cross the x-axis at each x-intercept? Well, remember that each of these zeros corresponds to an x-intercept. The -1/2 corresponds to an x-intercept at -1/2, 0. And because the multiplicity is 2, which is even, the graph touches the x-axis there. So we would say that it touches. Okay, and again, that's because of the even multiplicity. On the -4, that corresponds to an x-intercept of -4, 0. And at that x-intercept, the graph has, or the function has odd multiplicity, so the graph must go through the x-axis there, or crosses it. Okay, so it touches the x-axis at -1/2, crosses the x-axis at -4. Then in part C, it says determine the maximum number of turning points. Well, remember, the max number of turning points is always one less than the degree. So I need to look at the degree up here. The degree is the sum of the powers on the exponents, or the sum of the multiplicities. And in this case, it would be 5, right? So this is a degree 5, which means that the max number of turning points is going to be 4. It's one less. Okay, so max number of turning points is going to be 4. Has to be one less. So that means the graph turns at most 4 times. It could be less than that. It could be, anywhere from 0, 1, 2, 3, or 4, but it's got to be at most 4. Finally, it says determine the end behavior. Well, the end behavior, remember, is the power function that represents the tails of the graph. Okay, it's a power function that the tails represent. But in between, there's all these turns that could happen where on the power function, it's going to be smooth in the middle. Okay, so determine the end behavior. Well, I know right away the end behavior is going to include an x to the 5th power, because that's my degree in the polynomial. Okay, so the power function is going to have an x to the 5th. What I need is the coefficient, the leading coefficient. To get the leading coefficient, I have to multiply the leading coefficient that's outside of the factors along with all of the leading coefficients inside, and them raised to the corresponding powers. Now the ones on the inside are all 1. Right, they're all 1x and 1x. So when I raise those to their powers, they're all 1. 1 times -2 is -2, and so my power function is -2x to the 5th. That tells me what my end behavior is. My end behavior is the power function -2x to the 5th. Okay. Now, if you think about what that looks like on a graph, x to the fifth with a negative coefficient is going to look something like this. X is going to be a decreasing function, hence the negative coefficient, and the tails are going to go in opposite directions. Now in the middle here, like I said, there could be a bunch of turns going on. We don't know exactly what's going on in the middle. The power function would have that smoothed out. You know, it wouldn't have a max or a min anywhere. It would just kind of level off for a point and then keep going. But negative 2x to the fifth is technically the end behavior. This is what we'd be looking for. It's the power function that represents the tails.